The line segment AB is the diameter of a sphere S. Let's just draw a little sketch of this. Here's the center. There's AB. And the point C is any point on the surface of S. Let's put it here, for example, to start with. Explain why the dot product of AC with BC is equal to 0 for all possible positions of C. So it's got to be that this is 90 degrees. Actually, you might be able to spot, I mean, it's not technically a circle, it's a sphere, but it's going to be the angle in a semicircle circle theorem that we use here. Just need to explain it. So ABC will lie on a circle within a 2D plane. And using the angle in a semicircle because we know that AB is the diameter. Theorem. Angle ACB must equal to 90 degrees. And it follows, therefore, that AC dotted with BC equals 0. Now we're not actually quite done because there's a special case. And we should have probably said right at the start. So the first case, wait, let me call this case 1. C is not A or B. Because actually it could lie in the same position as we said, we're asked at the start to show that it could be any point on the surface. Case 2. Easy to miss this one, it's got to be said. C is A or B. But if that's the situation, let me just draw a little sketch over here. Then say this is B and this is A and C at the same time. Then AC in my case would actually be the 0 vector. So AC or BC must be 0. And then AC, so they're not perpendicular, but it's a 0 vector now. So AC dotted with BC will equal 0 here too. Just going to say proof, well, it says explain why, therefore AC dotted with BC equals 0 for all C. The mark scheme has a much more complicated, I mean, they go with this one, but they have a more complicated reasoning as an alternative. I'm not going to talk about that. I just think this is definitely the way to go. Probably, I mean, I just have gone straight for the fact that, yeah, if the angle is 90, the dot product is 0, but because it's an explain question, probably should have said a little bit more. It's going to be modulus of AC times the modulus of BC times cos of angle, cos of 90. And that is why it's going to equal 0. I feel like, yeah, I've clarified a little bit more now. Okay. Then we're now given the points A and B and C and asked to determine the possible coordinates of C. So let's draw this out. I can create a position vector A, which is 11, 12, minus 14. And then a position vector to B. Remember, this is still the same situation. This is still my diameter. B, I've got 9, 13, 6. And then I've got C over here. We know that the dot product between A and C and B and C, wait, is that what it was? AC, BC is 0. So, okay, let's work out what AC is. To get from A to C, I'm going to go backwards. I'm going to go minus OA plus OC. So it will be 2P minus 11, P minus 12, 1 minus minus 14, 15. And BC, similar reasoning, is going to be 2P minus 9, P minus 13, and 1 minus 6. So now we know that AC dotted with BC is equal to 0 from part A. Let's apply the scalar product. So we times the components together. It must be that 2P minus 11 times 2P minus 9 plus P minus 12, P minus 13, minus 75 is equal to 0. Multiply the brackets out, 4P squared minus 18P minus 22P plus 99 plus P squared minus 25P. 12 squared is 144. If you add on another 12, you get 156. Minus 75 equals 0. We're going to get 5P squared. This is minus 40P minus 25P, so minus 65P. Then 99 plus 156 will give me 255. So if I minus 75 from that, I'm going to get 180. Divide through by 5. Then try and factorize. They're going to both be negative if this is going to work. We need one of them to be odd. So minus 9 minus 4 works. And that gives me P equals 4 or 9. And then finally, we want to work out positions of C. So I just got to sub it back into 2P, P1. So C is going to be 8, 4, 1, or 18, 9, 1. Those are my two possible positions. Again, there's alternative ways to do that, but this is a pretty solid method, so I'm not going to go into any more. Have a look at the mark scheme if you're interested. And well done on this question.